Thank you. So first of all, thank you very much for the introduction, and thank you for the organizers for, first of all, organizing the summer school, as a result of which I hope, I should also thank, by the way, all the participants who went through my mini course, and they're still here. But as a result of which, not everybody I know, but as a result of which those who went through, will see some of the things towards the end for the second time. The talk will be a bit sort of going backwards in that start with the actual problem, which is the quasilinear wave equation. And then we talk about the nonlinearities. And then I talk about, so as you know, nonlinear problems, small data nonlinear problems are basically linear. I mean, the thing to really want to understand is the linear problem, but of course you have to do it the right way. And then to understand the linear problem, so that's what this mini course was about, we use microlocal analysis. Now, there are some catches always along the way. But anyway, and so this is joint work with my student, Peter Hintz, who is really more than a student. I mean, he's really a collaborator on this project. And in particular, some of the key parts of dealing with quasilinear equations is really a separate paper of his. So just do OK, so let's set this up. So I'm not going to write down the Kerr de Sitter metric, but Mihalis didn't write down metrics either, so I can feel good about this. It's a Lorentzian space-time of 1 time and 3 space dimensions, and then it solves Einstein's equations with a cosmological constant. And so it models a rotating black hole with some mass and the cosmological constant. So the black hole is the Kerr part, and the cosmological constant is the de Sitter part. So I will say a bit more about this without saying what the metric is. But what I want to describe is how to solve on this space-time globally and describe the asymptotic behavior of solutions of certain wave equations for small data. And so the advance in this, so the advance meaning in particular over Peter Hintz's work, is overcoming the normal hyperbolic trapping that Simon Dyatlov has told us almost all about by combining microlocal analysis and the Nash Moser iteration. Now, Nash Moser is not the thing you want to use in ideal circumstances, as Mihalis said, but it's not so bad, and it gives you results, so that's good. Anyway, so I should describe Kerr de Sitter a bit more precisely. So, I mean, by a bit more precisely, what I mean is that I want to describe the framework you should put yourself in when you want to think about the way that Peter and I thought about this. So what you do, you start with, you want to, it's, of course, a non-compact space-time as usual, or space, let's just put it, as one usually thinks of it. But let's try to think about it instead as something that's at least partially compact by adding a boundary at infinity where we want to do uniform analysis. Of course, this you could just get rid of, but it makes for nicer pictures because the picture is going to be compact anyway. And also because this really forces the uniformity of the analysis. So the picture you want to have is that you really want to think of a manifold with boundary, which I'm calling M, and then this M circle is its interior, and the boundary of it I'm calling X. So in the picture, this whole picture, I mean, below this top line, so this would be the boundary, this would be the interior, and so this is the boundary X up here. So the whole picture, including these regions here. But this is non-compact. This is supposed to continue somehow indefinitely or until you run into some singularity that Mihalis talked about. But we want to forget about all these extra complications. And so we want to work in a compact region, which I'm calling omega here. And it's just going to be bounded by some hypersurfaces, which I'm thinking of as, they're calling H1 and H2. I'm thinking of as level surfaces of some functions, Tj, T1 and T2. And so this H1 is some T1 equal to 0, and T1 is positive on this side. So I just want the T's to be positive in the region omega. T2 is 0 here, and is positive inside. And they're supposed to be linearly independent where they intersect, the differentials, that is. And then so the way you're supposed to think about this is this, I think it might say in the next slide, this H1 is going to be your initial Cauchy surface, and this H2 is sort of a final Cauchy surface in some sense. So here's a more honest picture of what Kerr de Sitter looks like. So I mean, it's supposed to be 4-dimensional, which I certainly can't draw. So the way this looks is this H2, which was the sides, the sort of final Cauchy slices, are the sides of a cylinder. H1, which was the initial Cauchy slice, is sort of the bottom of this cylinder, and the actual boundary X of this partially compactified space is sort of the top of the cylinder. So in terms of coordinates, I mean, I'm not putting coordinates on this, but if you really did put coordinates on this is sort of the this Eddington-Finkelstein coordinates that Mihaly mentioned. All right, so so you want to think about a Cauchy problem, so or something related to it anyway. So imposing vanishing Cauchy data at this initial surface H1, and then you can always, certainly for a linear problem, you can always convert general Cauchy data into this. For a nonlinear problem, you have to juggle things a bit, but essentially this does what you want. So I'm just going to think of vanishing Cauchy data. So of course, I'm going to instead have some forcing to get some non-triviality in the equation. And so what the framework we want to think about is, so like what sort of things we estimate, what sort of function spaces we have, and in fact, what should the equation even look like? So this involves what I call totally characteristic vector fields on M. So these just means vector fields tangent to the boundary, let's just say to the boundary of M. So in other words, I mean, locally, if you have a manifolded boundary, you just have local coordinates. I'm calling x the defining function of the boundary, or a defining function, I should say. And then the yj's are some coordinates along the boundary. And then these vector fields tangent to the boundary are just linear combinations of x dx and dyj's with smooth coefficients. So these are called, these are named VB by Melrose for B standing for boundary. OK, so the vector fields that we are thinking about are smooth combinations of these. And so then if you think of the dual metric, so that's composed of such vector fields, so just symmetric tensor products of these vector fields, so x dx's and the dyj's in various combinations. And then the actual metric, which is the dual of this, just involves then the dual one form, so like dx over x and the dyj's. And so in particular, the Kerr de Sitter metric is some combination of these sort of things, where again, x is just a defining function of the boundary, and the yj's are various coordinate functions along the boundary. So one could write this down, but it doesn't really help. So I also going to sometimes write this B differential, so it's D with the B on it. And so you see, there's an x here and there's an x here, so these just cancel, right? So this is doing really nothing in some sense. This is just the usual differential. But what it means is I want to think of the differential as so it's in particular invariantly defined. But I want to think about it as mapping into one forms which are of the kind that correspond to this structure. So it's keeping track of the one forms, or dually, it's keeping track of the sort of derivatives that you want to have. So if I have, say, some coefficient that is supposed to depend on u and the derivative of u, if I write it this way, that means that it has only these tangential derivatives to the boundary in it. All right, so then somewhat more precisely, the equations you want to consider are equations that look like that. So box of G, so G is the metric. This depends on this unknown u, or possibly even on the derivative of this unknown u. And again, whenever it's a derivative of the kind we just discussed. And then there's a right-hand side, which is some nonlinear expression in u and the derivative of u, plus some forcing. We need the forcing because I'm just getting rid of the Cauchy data to make life easier to present. And so the right-hand side, this Q, the nonlinearity, is supposed to be some, for simplicity here, it's supposed to be some some polynomial nonlinearity involving so products of, I mean, it's powers of the function u, and then some products of some vector fields applied to u. And again, these vector fields are the kind of vector fields we discussed, so tangent to the boundary. And then some smooth coefficients I'm adding only in case there were no vector fields, which are actually, that case is ruled out in the theorem I'm going to state first. So the first theorem with Peter Hintz is the following. So if you take alpha positive, so this alpha is a decay rate, And you take small angular momentum for this Kerr de Sitter black hole. And you take all these NJs. So these are the number of vector fields you have in the product, at least one. So you have a sum of terms, but in each of these, at least there's one vector field applied to you. So I explain why this enters and also when this is irrelevant. Then, and I'm going to state this in the least technical sense. So there's really no least technical case. So there's no complications of spaces and things like that. So if you just impose, say, some smooth complex support to them, and you have sufficiently small norm of some order, in this case it's going to be H14 norm of F, then in fact this wave equation has a unique forward smooth solution in the interior. And the solution is of the form that it's a constant plus some u tilde, where this u tilde, so remember x equals 0 is the boundary, so x to the minus alpha times u tilde bounded says that this u tilde is decaying as x goes to 0, where this u0 is just some, essentially a constant. So this chi is just some cutoff that's identically 1 near the boundary. So what this says in particular is that, again, this is, I'm going to state it in a much more natural way, but what it says is that solutions of this equation, so the equation on top, at least with small f, where small is in this particular norm, decay at this rate, x to the alpha, to constants. So just to connect in terms of usual time variables, so the usual time variables would usually be some like logarithms of this x. So this is really exponential decay in the sense that Mihaly talked about polynomial decay. So this is exponential decay to constants for this quasilinear equation. Right. So it's basically just a product of u, powers of u, so products of factors of u, in other words, and vector fields applied to u. So it's polynomial in u, and it's first derivatives, but the first derivatives have to be this tangent to the boundary kind of derivative, and then the coefficients are just some smooth coefficients. Yeah, sure. So I mean, you could have things like, you know, x dx u squared times, I don't know, u cubed, and then you could have a coefficient. Oh, in terms of standard coordinates. So you I'm not sure which the standard would be. So I mean, this is I mean. Okay, I mean, this is basically Eddington-Finkelstein. So x is really just sort of exponent. I mean, so certainly away from the event horizon, this would just be you can think of x as e to the minus time in Boyer-Lindquist. But of course, as you go to the event horizon, it gets sort of distorted. So I mean, it's easier to say it in Eddington-Finkelstein. Right. So then this y is basically just the angular variables plus I mean the sort of theta and phi plus plus the radial variable. This is, I mean, this is very well. I mean. Okay, so the way I think of this is that when you talk about a PDE on a manifold, then you start by saying that you're going to talk about the smooth manifold. I mean, at least you're going to have some regularity of it. And so this is sort of analogous. You sort of you specify a setting. I mean, you're not talking about the manifolded boundary, so you have to decide about what sort of structure you're going to have. And so the structure here is that you're going to think of so you want to think, first of all, specify the smooth structure of the manifold. And then you're going to have the sort of I mean, on an open set in Rn, there's no question what sort of vector fields you should think of, just smooth vector fields, or I mean, vector fields some regularity. And so this is sort of the analog of that. So it's very flexible in this sense. But you know, so of course, because now there's an extra structure and there's a boundary, there are things you can do. So for example, you decide that I think that this is a very strong function, this x, and I'm going to take its logarithm as my new smooth structure. So that's a very different kind of thing. And so that's the sort of thing that should mess up exponential rates of decay if you add terms like that to your operator.
You look at the transversal derivative to the event horizon, the regular transversal
Yes, you can certainly differentiate across the event horizon. Yeah. So the picture is right. So here would be your. I mean, I sort of like this picture more. So here's the event horizon and the cosmological horizon, and certainly can differentiate across this. But you have to be tangent to this infinity in the time unquote variable, and that's what it amounts to. Yeah. So yeah.
But in the standard coordinates, this tangency is just you can take partial t.
Right. So that's what I said. So if you translate this into if you take logarithms instead of x, so you work with e to the minus t would be the or this is like t star or something. This the Eddington-Finkelstein version. Then it would be like dt is what it would amount to, dt star. Whatever.
Yeah, but what's more natural is to think of the case of constant in a product by the t star is conjugate to the event horizon. So it is transverse to the event horizon and thus constant in a product
I would have to think of what that exactly does to. Yeah. Yeah. Right. All right. So. Right. So certainly you have perfectly nice. I mean, the metric is non-degenerate in this form. So taking duos is not really an issue. So anyway, all right. I mean, the metric is a non-degenerate Lorentzian metric in this space, and so this is somehow the natural thing associated to it. So that's how it is. All right. So if you look at the Klein-Gordon equation instead for a change, so I just added the mass, but the same equation, then you have the analogous conclusion without the U0 term. So this was the constant that we were decaying to, and without the requirements that you have to have at least one derivative in the expression. And this is basically due to the absence of a zero resonance. So this is related to things that have come up earlier today. So I will say more about this a bit later. So basically the only reason why we have a small angular momentum is really to exclude possible resonances in sort of Semyon's terminology in the upper half plane. So this sigma would be the analog of Semyon's spectral parameter, which I don't remember how he denoted it. But anyways, in the upper half plane, apart from the zero resonance, which comes from constants, I mean, constants solve the wave equation, linear wave equation. You don't want to have any resonances, and so that's how this smallness enters. So basically, I mean, there's some limitations, but certainly no smallness limitations on other parts of the framework. But if you have, if somebody proves that there are no resonances in such in this upper half plane apart from zero, then everything goes through. So, what this says that the main constraint on the solvability of this nonlinear problem is resonances. I mean, this is not to say that that's the hardest part. It's not at all the case. It's somehow it's really no trouble. It's finding many resonances. It's no trouble in terms of putting things into a framework. But unfortunately, what do resonances do in the wrong half plane? They correspond to growing solutions. So now if you have something like polynomial nonlinearities, you square something growing, it's going to grow even more. So this gets to the point where the nonlinearity starts driving the equation rather than the other way around. So this is this morning's talk in some sense. So that's the sort of thing that you don't want. So, I mean, there's nothing scalar about this setup, really. It works equally well for vector bundles, so such as, say, Maxwell, or even Einstein if you add gauge conditions. The only real thing that's troublesome here is the resonance part. And of course, if you add gauge conditions, then the chances are that you are doing it not quite the right way, and then your gauge condition gives you extra resonances, so which might really be in the wrong place.
You are also assuming that the number is cosmologically small.
So no, it's. I mean, really the.
Because you are assuming A.
Right. So there's no smallness on the cosmological constant. A small is just because the resonance analysis is easy to do for de Sitter-Schwarzschild.
Let's say you assume that lambda is small, you cannot infer the absence of resonance from what we have done.
So in fact, I did think a bit about this just before this talk, and there's a chance that one can do this. It would be very nice if one could, because if one could, then everything would go through in the for Einstein, and therefore small lambda. Yes, exactly. So because it's a bit funny. I mean, it's a very good question. It's a bit of a funny deformation problem, but it's the sort of thing that Maciej mentioned at in the first talk, that it's quite possible that one can get results on this. I mean, the problem is that sort of directly, I mean, Kerr de Sitter, if you look at any formula, is more complicated than Kerr. So it certainly would be very nice to not have to look at any formula. And finally, this sort of the general framework deals with analysis modulo finitely many potentially troublesome resonances. There's no really good way of excluding those finitely many potential resonances. So it would be very nice if one could get around this without real work. All right, so I mean, using somebody else's real work. So I want to say a more precise version now. For this more precise version, I want to just have some bit more notation. But I mean, this is sort of the natural notation that continues. So I want to say this L2B space, which is the L2 space relative to the density of any Riemannian-Lorentzian metric of this kind. So in other words, in local coordinates that I wrote down, it just looks like a smooth multiple of, I should have said a smooth multiple of what's written down there. So it's dx over x is, again, it's like d log x, and log x is this time, quote-unquote, variable. So that's sort of the natural L2 space in some sense. But then the derivatives that enter are, again, these B derivatives. So the Sobolev space HSB is just consists of elements of L2, at least for I'm only defining it to make it easy for non-negative integer orders for functions in L2, which remain there if you keep applying to them vector fields which are tangent to the boundary up to the order we want. And then we also want weighted Sobolev spaces with these weights x to the r. And so this, again, for r positive would mean exponential decay. For r negative, it would mean exponential growth in the usual terms. All right, and then at this point, it's sort of natural to sort of relax a bit the requirements on the coefficients, because really C infinity is not the most natural space in this context. What's more natural is these conormal functions. So these are just this h infinity. So these are functions which are in L2 and remain so if you keep hitting them with vector fields tangent to the boundary. And you want to do similar thing with the vector fields. And then the forcing, you want to, again, the natural thing is to make it similar. So, I mean, I'm going to state also the finite order version. But anyway, the infinite order version is just that you are in a conormal space, which is decaying. So in other words, this forcing is a decaying at the boundary, so future infinity, quote unquote, is decaying there at this rate alpha, so it's an exponential decay, and it keeps remaining there if you hitting it with iteratively up to all orders actually with vector fields tangent to the boundary. Okay, so that's the forcing. All right, so the theorem in this more natural setting, in terms of there's more things to explain, but they somehow fit more naturally with the way everything works, is that if you have small, I don't know, H14 alpha norm on the forcing, then the solution, in fact, has the form of a constant, well, times the cutoff, plus something that's in this conormal space, H infinity alpha. So again, it's decaying at this alpha rate with all derivatives. And then the difference between Klein-Gordon and wave is, again, the same, that you need at least one derivative without the mass, just because of the zero resonance, and you get in the massless case you get decay to constants. You can always, I mean, sort of if you look at the Nash Moser argument, you can always get a finite order version of this. So, but I mean, it's going to be very lossy. So as I said, the main problem for solving small data problems is solving a linear PDE, but you have to be able to handle it. depending on, so that it interacts well with the nonlinearity. And so the way we are looking at this problem is to solve the PDE globally, modifying these, basically working with the Sobolev spaces, but modifying them slightly. So I mean, the moral is you sometimes think of this PDE as just as if it were an elliptic PDE. I mean, an elliptic PDE you wouldn't try to solve it in some small domain. You would have to globally solve it. And you're sort of thinking of it in sort of analogous way. But of course, you lose it. I mean, the PDE loses derivatives relative to elliptic equations. So, so these modifications that I mentioned that we need, they add some support conditions. I mean, you're trying to solve a Cauchy problem, not just have some random solution of the equation. And you have to also take into account that at least for the actual wave equation, the solution is going to be asymptotic to constant. So you somehow have to have constants in the space. So we're actually going to look at spaces like this. It's just this Sobolev space plus C. Now this dot bar is I'm afraid, Hermander's notation. So what this is that the dot corresponds to supported distributions in so remember the picture was this. It's probably good to have anyway. Here's my X, that's the boundary. Here's my H2, H1, and this is omega. So what this space is distributions which are extendable at H2 and supported at H1. So in other words, you can think of them as a distribution in this bigger space, which is actually has support in the correct half. So in other words, they would think of them as being 0 on this side. And they just extendable distributions, or if you sort of tempered distributions at H2. But so, of course, within this Sobolev space. So it's just convenient to formulate the Cauchy problem in sort of microlocal analysis terms. All right, so we're going to look at nonlinear equations. So we're going to have some multiplication, and we have to deal with that. And so what you have to remember is that the Sobolev spaces, and then also this space, in order for this to be closed under multiplication, you certainly need that the decay order is greater than or equal to 0. I mean, you don't have growth. That's sort of very bad. And that you have at least n over 2 derivatives. And then the Sobolev spaces form an algebra, so you can multiply. And then the same thing happens if you modify it this way. Now, in terms of derivatives, the best case scenario for just the linear inverse of the linear wave operator is the loss of one derivative relative to elliptic estimates, because that happens even locally. But the other main linear obstacle is trapping, which actually Semyon discussed. So in fact, you know all about already. So maybe I can skip it when we get to that. But anyway, so examples. So again, this is just for the linear operator. What you have is if you look at de Sitter space, so this means no black hole, then because there's 0 resonance, the best estimate you can have for box inverse on these spaces. So remember, this X is really just the Sobolev space with the same indices, except you throw in constant. So the best thing you can have is the gain of one derivative and no modification of weight, because that means the loss of one. It's a second order operator, so it really means the loss of one derivative relative to elliptic estimates. And so this holds for R positive small. The small is only entering because, so R positive means decay, and the small is only entering because I have to, in order to get this, you want to have a statement that there are no resonances other than the 0 resonance above imaginary part sigma equals to minus R. So I'll get to that a bit later. OK, so for the Klein-Gordon equation, so what happens if you go from the massless to the massive case? Then the only thing that happens is that there's no resonance in the closed upper half plane. So what that means is that this inverse on these same spaces, except you can drop the constants from the right-hand side, is going to be nice and bounded for suitable small decay rate. So I should say that you can, if you're willing to make your spaces more complicated, you could always add finitely many resonances and get more expansion. For Kerr de Sitter space, the difference is that there is trapping. So in addition to the resonances. So what this means that if I keep my target space the same as for the wave equation, and then I lose an extra epsilon derivative on the domain. And so that's what I have, again, for sufficiently small R positive. So the decay rate is sufficiently small and positive. For Klein-Gordon, the epsilon remains because that has nothing to do with the resonance. There's something to do with trapping the loss of derivatives, but you can drop the sum and correspond to the resonances. So that's a basic linear picture. And then, so the simplest setting for a nonlinear equation like this is if actually if it were semilinear, so box is just box of G, and G is fixed, because then you could just run a Picard iteration, or the contraction mapping principle. I mean, this is sort of the semilinear equations are sort of equivalent in terms of what you can do for fully nonlinear elliptic equations, like run Picard for small data, that is. Right, so in the semilinear setting, you can just run Picard iteration, and then everything is going to be fine because box inverse loses the derivative, but it's only a semilinear equation, so everything is fine. Now, now you could not certainly put in here a box of GU du to run this argument because of the loss of a derivative relative to elliptic estimates. But if you have trapping, then you have even further losses of derivatives. So if you try to run Picard, then even a Q that depends on the derivative of U would not be allowed. All right, well, there are ways around this. So if you look at now quasilinear equations, so here now the G depends on U, but not on derivative of U, and Q is allowed to depend on derivative of U. But let's forget about trapping losses. So this is like de Sitter space. Then you can instead run a modified sort of Newton type, at least as far as the second order level is concerned, the second order terms, that's what I mean by this, is concerned method. So what we're doing, actually this is Peter Hintz's work, what he was doing is inverting box of G of UK, so the kth level of the iteration, and applying it to the right-hand side to get UK plus 1. And then you can get from this that sort of well-posedness in the appropriate sense in Sobolev spaces. So but what this requires is a global linear theory for operators with the Sobolev space coefficients. And so this is exactly what Peter Hintz has developed. So I should say this is there's earlier work from the 80s of Beals and Reed on exactly these sort of things, without, of course, the B and the decay. So just the usual setting of manifolds, no boundaries, no infinity, sort of local theory. All right, so for quasilinear equations on Kerr de Sitter, then there are these trapping losses. So so we will need to run. I mean, we'll need to run a Nash Moser iterative scheme. So I mean, we don't want to make this complicated. You're losing derivatives. You're doing Nash Moser. So you want to run the simplest possible Nash Moser you can think of. And there's this beautiful paper of Saint-Ramon on Nash Moser iteration, which is very short. So I definitely recommend as a good reading. So this is like a regularized Newton iteration scheme. Maybe I'm not really going to say more about this, but it's all really pretty straightforward. I mean, one thing I should say is that, as he says in the somewhere in the paper, this is probably the worst result in the literature in terms of number of derivatives lost. But I think he, I mean, the amount of clarity that was gained by this was sort of worth it. Anyway, so it's a very clear paper, and so that's what we're going to use. Now, the input of Nash Moser DAO is the following. So we need, first of all, linear theory for this HSR coefficient, and a bit more. So just to run Peter Hintz's sort of Newton type method, what you need is sort of continuity results for the multiplication operator, and of course much more, but this is the easiest thing to illustrate. I mean, you want to run this. You can think of this as happening at the level of products of symbols in compositions of operators. But then also you need similar things for Schwartz kernels and sort of other stuff. So on the basic result of on the continuity of multiplication and Sobolev spaces is that the product is estimated in the Sobolev norm by the product of the Sobolev norms up to a constant factor. But what one needs to run Nash Moser is a tame version of this estimate. So let me just say it in words. What the tame estimate is doing is that you think of having two scales. You have a high regularity norm and a low regularity norm. So high is S, low is S0. And then what you want is an estimate like this, where the high regularity norm of uv is estimated by the low regularity norm of u times the high regularity norm of v plus the high regularity norm of u times the low regularity norm of v. And so this is, of course, a stronger version of this for this multiplication is Moser's estimate. So it's sort of these sort of things that what you need also for things like L2 bounds for operators and various other things. But if you prove, for example, your estimates in your linear theory by things like positive commutator estimates, just look through your proofs, these sort of things will be automatic. So it's not like you have to work hard to get them in this form. All right, so now to the linear analysis, that now that we at least think we understand the nonlinear bit. So there are two bits of this. So corresponding to these two orders on these subalef spaces. So there's a regularity analysis. So this is like derivatives. So like how can you control derivatives? And so I'm calling it B regularity analysis because this just means that the derivatives they control are these tangent to the boundary derivatives. So that's all it means. So you are doing the control in terms of the regularity order, this S order of subalef spaces. So what this means is that you want estimates of the form that's written there, that you control U in some subalef space HSR in terms of LU, so L was the operator, like the wave operator, in some subalef space HS prime comma R. So R is the same, the decay order is the same, but the derivatives order is shifted to whatever, plus an error term, this other U of HS tilde R. R is again the same, so there's no difference in decay, but with S tilde being less than S. So often it's going to be arbitrary, actually, for linear theory. So normally you think of this, so if this R weren't there and you were in a compact manifold and say you were thinking of an elliptic operator or something like that, then this would be a sort of, you think of this last term on the right-hand side as a trivial term corresponding to the compactness of the inclusion of the space on the left-hand side into the space on the right-hand side. And so this is the basic thing for Fredholm theory. So everything is nice and easy. But unfortunately, in this setting, there's no compactness of the inclusion because you also need to get decay in the spaces. So that's the extra bit. And so that's one half of the one of the two parts of the linear analysis. And the other part is what I call this normal operator analysis, which provides a framework for understanding decay and asymptotic properties of solution. And this is where the resonances enter. All right, so to be a bit more concrete, if you have let's just write down a differential operator. So there's a concrete, nice linear differential operator, second order. Then what Marrows actually called the normal operator just means that you freeze its coefficient at x equals 0. So of course you need to trivialize things to make sense of this, strictly speaking, near the boundary. So just freeze coefficients, and if you froze coefficients, and you can really think of having the whole real line, half line in x floating around, and then this is a dilation invariant operator in the x variables. So if I went to log x, like Semyon wants me to do, then this would be a translation invariant in this log x t variable. Right? And then the natural thing to do would be to use the Fourier transform. If you don't do that, then it's a Mellin transform. So Mellin transform, and all that the Mellin transform does, it changes x dx to a multiplication by this dual variable, which is sigma. So if with the Fourier transform, you would still get sigma, but it would be in the usual dual variable of dt, however you call it. OK, so now as I said, the first part is a regularity analysis, which I will say more about in a moment. But what it does automatically is that it gives you uniform control for this L hat. So this was this Mellin transformed normal operator. So it gives you uniform control of it as this Mellin parameter sigma goes to infinity in strips, horizontal strips. So the imaginary part of sigma is less than c. So this is basically it's closely related to what the picture that Semyon was talking about, and certainly control of things like trapping is one part of getting that. So what I want to say is that in strips like, so this is going to be the complex plane in C, I mean in sigma, and so so you care about what happens in, say, strips like this. So in strip like this, you have good control near infinity. by the derivative analysis, by so regularity analysis. So why? Well, this is very easy to see why, because this sigma is just the dual variable of x dx. So having regularity, in particular with respect to x dx, corresponds to sort of statements about this L hat for real part sigma large. But the extra issue is that this L hat sigma inverse, this is a nice meromorphic operator, but meromorphic does allow some finitely many poles, whatever those are, even in such a strip. So these are the resonances. And so for Fredholm theory, what you need is, so again, we have a nice linear operator at this point. It's smooth coefficients. And what you need for Fredholm theory is to choose weights, so these are the orders R, such that there are no resonances on the line where the imaginary part of sigma is minus R. So if I, for whatever reason, decide that I really want to work with this sort of weight, so this is now minus R, so im sigma, sorry, equals minus R. This is my line. So I should choose this line so there are no resonances on it. So there could be some below and some above. So, but none on it. So if I do this, then I actually get a nice Fredholm problem. Now, so just to be a bit more concrete, if you're in an elliptic setting, so this boundary acts for a compact manifold without boundary, then what would happen is that L hat would be an operator from HS to HS minus 2, a second order operator in this case, a nice elliptic operator. So they have a beautiful Fredholm inverse going the opposite way. I mean, meromorphic inverse. And so this, for example, happens in spaces with cylindrical ends or asymptotic Euclidean spaces. Now, in our setting, we lose a derivative relative to the elliptic setting. And so what happens, the way you can set this up, is that you think of this operator as going from HS, and then you have to put in this boundary condition, so that this minus corresponds. So it's really only the H2 that's left, right? We have manually transformed the operator in the x variable. So this is gone. We are working on the space big X. And the only piece of this boundary of omega that's left is this H2. So we have some boundary there. And so anyway, roughly speaking, the way you want to think of this operator L hat is that it's mapping HS to HS minus 1. And the inverse is going to go backwards. But of course, it can't really do that. You have to add an extra condition. That's a perfectly nice condition still. It's like a sort of first order in that one operators put in their coisotropic condition. Anyway, it's a very well-behaved space, a perfectly nice Hilbert space. But the one thing to notice is while this operator enters on the left-hand side, the space you get is actually independent of sigma, because the principal symbol of L hat is independent of that. And so, in fact, you get an analytic Fredholm family, which is what gives you this meromorphic inverse. All right, so okay, so let's step back again for a moment and let's think about elliptic problems in the whole space M now. So beforehand, that what happens if you have an elliptic problem on the boundary? Okay, so what happens if you have an elliptic problem on all of M? So an example of this could be, again, something like a cylinder, so cylindrical ends, or other would be actual Euclidean space. So what happens in these settings? So if you choose this weight R, so there are no resonances sigma, with the imaginary part sigma is minus R, then this operator L is Fredholm between these weighted spaces. So again, it's just closed range, fine dimensional kernel, fine dimensional co-kernel. Now you can make this into an honest invertible operator if you just add to this sort of resonant states. I mean, there's a fine dimensional, right, when you're talking about Fredholm operators, there's a fine dimensional failure of invertibility. And so you can adjust this by adjusting the spaces a bit, just in a fine dimensional way. All right, so in our non-elliptic settings, we always lose a derivative. So the typical scenario that we would have is that this operator L, again, acting from a weighted space to a weighted space, again, we lose a derivative, and then you have to throw in, so it's not quite a weighted space on the domain, because you have to throw in this extra condition that LU is in HS minus 1R. So this operator is Fredholm. All right, so I mean, this is by typical, maybe typical meaning typical in the ideal world. So this works for all R if there are no resonances on the line, imaginary part sigma is minus r. If either there's no trapping, I mean, it works for all r if there's no trapping, period. And if there's normally hyperbolic trapping, then it actually still works if you're working in spaces that grow at the boundary. So this is what Semyon was basically reducing to in his talk by this theta plus operator moving to the upper half plane. So in the upper half plane, you get real principal type estimates regardless of trapping. So that's the ideal situation. Okay. Now, all right. So if you now look at the wave operator with or without trapping, either way, when this order r is negative, then the inverse is going to be a nice map from s minus 1 to r, s minus 1 comma r to s comma r Sobolev space, and then if you want to go to positive orders, so decaying orders, which you need for the nonlinear equation. I mean, for the linear equation, you say, why not just work in negative order spaces? And then you can use contour deformation argument to get expansions. But for the nonlinear equation, you really need the algebra property. So you really need the decay. So what you can do is just add the resonance spaces. So in this case, the only resonance is the zero resonance, just complex numbers. And you get a nice inverse again, if you don't go too far, if there's no trapping. Now, the trapping losses, I should emphasize, are all as this sigma, this dual variable of the boundary defining function, so of time, really, in some sense, goes to infinity. So that still says that this family of operators we have on the boundary itself, so whose inverse is supposed to be meromorphic, and then the poles are the resonances. So that's still indeed a meromorphic Fredholm family. And what happens, though, and this is what Semyon was talking about, is that its high energy behavior is bad. It's sort of lossy when you let the real part of sigma goes to infinity, but the imaginary part less than or equal to 0. Uh-huh.
And you work in this framework,
Yes.
you lose derivatives and you still need a Nash Moser.
No. So you still, I mean, so yes and no, because you're two parts of the question. You still lose derivatives relative to elliptic equations. So that means Picard is out. But you don't quite need Nash Moser. So actually what Peter Hintz did was to run this modified Newton type method. So you can still do it. Right. So right. So I mean, you don't. So but you don't need Nash Moser.
But I thought that because of the R, because of the decay.
Oh no. So the decay is the decay is actually extremely. The decay is perfectly nice. Yes.
So it's only the trap.
It's only the trapping that causes Nash Moser. So I mean, it's not completely clear whether it definitely has to cause Nash Moser, that you're forced to use this. I think if you want to get exponential decay, you probably end up with something like that. If you want to live on the borderline, you might be able to wiggle. Seminar equation with nonlinearity in the derivatives. Yeah, so that's still fine. Yes. No. You just. Oh, you for which one did you ask? So for Kerr de Sitter, for Kerr de Sitter, even for semilinear with derivatives, we use Nash Moser. That's correct. Yeah. So we use Nash Moser even for semilinear if you have derivatives. Well, so probably it has something to do with the better decay rate that you get. So it's a question that whether you could get away with polynomial decay going so far. So see, what happens in the losses in terms of derivatives are bigger. The farther away you go from real sigmas, the bigger the losses are. So what Semyon said is that like the h to the minus 2, this is this is a uniform estimate all the way to its first string of resonances, and it's pretty optimal. So there might be like an epsilon in the conversion between wave and resonance pictures. But if you don't want to go that far, the losses are smaller. So in fact, they are just logarithmic, as Semyon mentioned, right on the real axis. And it's quite possible that these are the sort of things that, if you think about it from a wave perspective, so without doing a Malinter Fourier transform, they are fine. But so if you go a bit beyond, then your losses will be some definite amount, like at least an extra h to the minus, I don't know, a third, say. And so then, even if you did it in the wave equation, try to do the wave equation in a way, almost certainly there's going to be an epsilon, I mean, at most epsilon better than h to the minus 1/3, which is still a loss. So that's my, I mean, I don't know, but that's my.
But how? The results when compared to the linear equation, Sitter are strictly strong. I mean, that's to say one can prove bounded for in this regime.
You mean without loss of derivatives?
Without, I mean, if you follow.
Yeah.
You have more decay. So it should be the same result that can be.
Yeah, well, but we prove it's a stronger result in terms of the conclusion, right? So because this is proving exponential decay. So the question is, can you? No, but so what you had, but there's a reason why. There's a reason why. I mean, there are two reasons. I mean, there's one obvious reason why you don't want to run an unweighted space, so without proving exponential decay, which is that you would be running through a zero resonance, which is sort of against the general Fredholm spirit of this. So that's one reason why I would try to avoid it. And the other is it's not clear whether it will, how easy it would be to do this. So the thing is that it's not what's in the Kerr de Sitter setting. You can prove more, but it's not so clear if you could prove just what you want to have with the in a way that you don't lose derivatives. So I don't know. It's sort of incomparable, is what I would say. It's not clear whether you could do it otherwise. It certainly involves more work somehow to get to gain no exponential decay, but lose no derivatives, no extra derivatives. But it doesn't mean it's not doable. It's more work. So yeah, it's quite possibly, yes. Right. All right. So all right. So let's see. Did I go through this? Right. So the so what you need is so I set everything up as a sort of Fredholm problem, and then what you need is just a non-elliptic version of the usual Fredholm theory. I mean, usually Fredholm theory is presented in an elliptic setting, which is not really really necessary. So here's a quick reminder. So of microlocal analysis. So we use pseudo-differential operators. So this is just in the boundaryless setting, such as the boundary for right now, X. So use pseudo-differential operators to microlocalize. The principal symbol is just a function on the, well, you can think of them as just a function of the cosphere bundle, which you just think of as the cotangent bundle modulo minus the zero section modulo dilations. And then the wavefront set is just a subset of the cosphere bundle, while the characteristic set is just the zero set of the operator, I mean of the symbol A, and the elliptic set is its complement. So I mean for general orders it's similar. You just have to say a few more words, so I won't. So what elliptic estimates look like from this perspective is what's up there. Is that you can estimate, so there, I mean, these estimates are all the same kind, that you want to estimate U microlocally somewhere. So B1 is going to be some pseudo-differential operator localizing somewhere. In terms of, I mean, I have to use the equation. So in terms of PU, well, microlocalized by something, which I'm calling B3, and some, quote, trivial, unquote, error term. So this is this S tilde norm of H, some very low order norm of U. And so the elliptic estimate is that you can do that if you just take this B3 elliptic on the wavefront set of B1. And this is just, and the wavefront of B1 is disjoint from the characteristic set P. So this is just elliptic regularity microlocally. The real principal type estimates are just, on the other hand, is that you can propagate, so this is wave propagation, that you can propagate estimates from one point to another. So if you understand what U is like, so this is what I think Maciej-Zworski had pictures like this. If you understand what U is like, where some operator B2 lives, then you understand also what it looks like along the flow from it. So that's where B1U is. If you understand also PU in between. So B1U is controlled by B2U, where the two are connected by the flow, plus PU in between, again, modulo a trivial term. So this is sort of like Maciej-Zworski's picture. And so the basic problem with this wave propagation picture is that you need to control U somewhere. So I mean, it's a propagation result. You know U somewhere if you know it somewhere else, right? So where do you get the somewhere else? So the one way to do this is for Cauchy problems And so there, in this Hermander terminology, one would work with supported distributions, which is what I mentioned. But basically, you work with Cauchy problems. And then the initial data, so in this case, we say 0 initial data, control the solution. Another way to do this is instead to have sources or sinks for the flow, which is, again, what came up in Maciej-Zworsky's talk. So this would be at fiber infinity in the cotangent bundle. And then there you can get estimates, quote, for free, unquote, again, as Maciej-Zworsky mentioned. So this is also analogous, I should say, to Euclidean scattering theory, which I think will come up in the next slide. So, but one thing that's important in this case is that you have a threshold regularity, which I'm calling S0, which depends on the subprincipal symbol, or really the principal symbol of 1 over 2I times P minus P star, as well as the Hamilton vector field. And so as an example, if P minus P, so P was an order M operator, if P minus P star is order M minus 2, so 2 orders better than expected, I mean 1 order better than expected because P had real principal symbol, then this borderline regularity will be M minus 1 over 2. So for wave equations, M is 2, and then this borderline regularity would be a half. In scattering theory, the relevant order is decay at infinity. The relevant behavior is decay at infinity. The order of the Laplacian is 0 in that sense, and this will be minus 1/2, which is exactly the limiting absorption principle. Okay, so so I just wrote down, but maybe I'm not going to go through this. So I wrote down the estimates, which Maciej-Zworsky also mentioned in this radial point, this generalized radial point setting. So this source sink structure. In the high regularity setting, you have this free estimate in that you estimate U in terms of PU in the appropriately shifted space without having to control U somewhere else. While in the low regularity regime, you have to, so think of, say, you have a sink, the backward flow to this sink. You have to control U in a punctured neighborhood of the sink in order to control it at the sink itself. And of course, you still have to control the PU, otherwise you don't have an equation. All right, so the way this happens, so maybe I just quickly draw the diagram. Oops, I have 2 minutes. The flow diagram was, as in Maciej's talk, is you have, say, sources and sinks, and you have by characteristics connecting them. And so what you do is you can, if you're in a high enough regularity Sobolev space, you get regularity for free at one of these sets. And then if you're low regularity, you can propagate the estimates to these sets. All right. So in Kerr de Sitter space, this happens via a radial set. So this just means that the Hamilton vector field is tangent to the dilation orbits on the cotangent bundle. So there's no dynamics in the radial set. And so asymptotic Euclidean scattering theory is similar, so as in narrows this work. In Kerr de Sitter space, there's non-trivial dynamics within the radial set, but the normal dynamics is against source sink, so it doesn't really make any difference. And in both cases, these funny sets are the event horizon of the black hole or the cosmological horizon of the Sitter end sort of within the boundary. Okay, so here's the picture. So, so what's shown here is that these L plus minus are really the one of them is the cosmological horizon. The other one is the event horizon, just at infinity. So the whole horizons would be coming down like a cylinder. And so these are the things that normally sources, normally within the boundary X are sources or sinks. But as the diagram shows, if you think of the whole manifold, then they're actually saddle points for the flow. Just the difference within, say, a Minkowski setting. So if you do this, then the wave operator P. So actually, this is the normal operator setup as I'm saying it, and its adjoint has sort of Fredholm estimates on dual spaces, and so this is what gives the Fredholm theory. Now, the way this goes is that for the forward, so the adjoint of the wave operator, if you're trying to solve the forward equation, the adjoint is the backward solution, right? So for the forward solution, the control comes from the radial sets. For the adjoint, it comes from these, you're solving it backwards, it comes from these H2, so the Cauchy surfaces. Okay. Now, maybe just say it in a few words that if you try to run this now on the whole space M, so this is now this space-time, then everything is similar except that you have to use what's called the Beep pseudo-differential operators to macro-localize. So this is what I explained to some extent in the mini course, but certainly I won't have time for it now. Yes. So I won't have time for it now. And as I said, you get sort of saddle points for this flow. But anyway, at the end, you get these Fredholm estimates for both the operator and its adjoint. Now, if you have, these Fredholm estimates come if you have this a non-trapping assumption. But if you don't have, so like de Sitter space. But if you have trapping, then these estimates need not hold, and so this is because of the sort of the photon sphere, right, of Schwarzschild de Sitter space. So this is normally hyperbolic, and Semyon explained everything that you need to know about normally hyperbolic trapping. What happens though is that you get these Fredholm estimates, these nice Fredholm estimates, still for the growing spaces, for the negatively ordered spaces. And Semyon knows, explained, in part starting with the work of Wunsch-Dworsky, how to deal with positively ordered spaces, or what corresponds to them anyway, on the Mellin transform side. So this is what gives the lossy estimate. So this was done by Wunsch-Dworsky, Dyatlov, and others. In fact, saying Girard and Sjöstrand. This was done in a smooth or analytic setting, so that's a lot of structure. You have to remember that we can't do this because we're working on a nonlinear equation, so we can't really have and we are doing a non-Picard type iteration, so we can't do this. So the key point is that the linearized operator that we have to invert around some point u, which is not going to be just the actual, say, Kerr de Sitter metric, corresponding to the Kerr de Sitter metric, is that you think of it as sort of broken up into two. So the coefficients of the operator are in this good space, right? I mean, that's what we're trying to show. We're trying to show basically something like decay to this Kerr-like space. So they're in this good decaying space. So what we do is you really treat the second term, so the difference from Kerr de Sitter, as a perturbation. So for the actual Kerr de Sitter type metric, you can use Dyatlov's estimates, which is very nice in this setting. On the other hand, you can treat the difference between the two operators sort of directly, right? So remember that what I said is that when you're working on growing spaces, then all the previous machinery went through, even without dilation invariance or anything like that. So the upshot is that you get a tame estimate out of this for the solution operator. So here's the tame estimate just written out, and then this plugs into the Nash Moser framework and gives global solubility and the asymptotic, so decay to constants. So again, the Nash Moser just means that this estimate really just comes from everything except this work on normal hyperbolic trapping in the lower half plane. So Wunsch-Dworsky and Dyatlov works perfectly nicely. It's of positive commutator estimates. It works perfectly nicely even in this Sobolev regularity space setting. All the estimates are automatically tame. And since you are getting decay to essentially Kerr de Sitter, you can use the smooth results that of normal hyperbolic trapping into the analytic continuation regime to put everything together. So that's sort of the punch line. Thank you very much.